start again. Yeah, okay, but I think logarithmically, most of the shock is on the outer scale, or at least it does exist there. Now, this simulation was done for intermediate mass black holes, but if you extrapolate it to supermassive black holes, then you get that the energy dissipated by the shocks is about 10 to the 51 ergs. And this should ring a bell, because this is more or less the upper level of what we see. So, so what happened is that Yair Arkavi was here about a year ago showing the result that he had, and when the talk was, that was, I think, the first time I ever heard about tidal disruption events. And then when the talk was over, Tzvi told me, hey Gilad, I think you're not doing anything special right now, right? Do you mind doing some calculations? So we went down the stairs to Tzvi's office and desperately looked for an envelope, but there was none. So both of us went home to look for old bills or so, find an envelope. And then next day we met and we both brought our backup envelopes, and that's pretty much what we had. We had a black body radius of 10 to the 15 centimeters, a black body temperature of 3 times 10 to the 4 Kelvin, a total energy of 10 to the 51 ergs, and a line velocity of 10,000 kilometers per second. And this is indeed what we usually see in most candidates. In fact, there is even a bonus, because if what gives this signal is the outer shocks, then we naturally get a T2 minus 5/3, because nully shocked metal simply follows the mass fallback rate. And this is pretty difficult to explain in any other of the propositions, because, for example, if you take Eddington threshold, then we expect between a year and 3 years of constant luminosity due to the luminosity being cut at the Eddington level. Or if you take a mechanism with reprocessing, then there are so many proportions to keep in the way between the mass fallback rate and all the stages until you get some signal out of the reprocessing. And in the way, you have to ignore many, or to tune very well many factors. So it's not really clear how you get a T2 minus 5/3 out of all this processing. But there's of course a few caveats in this model. One is maybe the 10 to the 51 or 10 to the 50 is just a selection bias. So we know in the case of Yair that he was actually looking only for about 10 to the 50 between the ordinary 10 to the 49 erg of ordinary supernovae and the 10 to the 51 and 10 to the 52 of superluminous supernovae. So I don't know well enough about other searches, but it could be the case that we're simply only looking at the 10 to the 50, 55 ergs. And that's why we don't see 10 to the 53, for example. The same story could be with the T to the minus 5/3, because for two reasons, actually. One is that this has been the hallmark for TDE searches for many years. And another one is that you can sort of manipulate this power. You can change the T0, the time of the first orbit. If you're not exactly at the T to the minus 5/3, but say T to the minus 6/3, well, you can play a little bit with the first orbit and then get T to the minus 5/3. So maybe this is also a selection bias. But let's just imagine that we're 10 years ahead, and we've gathered a huge sample of TDEs. And let's also imagine that now we have TDEs ranging from 10 to the 49 ergs to 10 to the 53 ergs, filling all this gap. And we also have all kind of trends of light curves. So say from a luminosity, from a constant luminosity all the way to, I don't know, T to the minus 4. Would it even be interesting to try to find a common explanation to all of this? I don't know, I'm just raising the question. I know that an important motivation for our paper was the snapshot that we had at that time. We saw some similarities, and that gave us the idea. If we instead had a huge spread, I don't know if we would have any motivation to try to find a common explanation to all of this. So I think it's kind of an open question, and interesting to see what will come by. Another caveat is that while we were doing these calculations, we're assuming rather a circular flow, looking at the simulation. But then for supermassive black holes, the flow is probably more elongated, and at least in some of our calculations, we have to better adapt it to a more elongated flow. But probably the most interesting question is, where are 10 to the 53 ergs hiding? If what we see is the shocks, and we think it is the shocks, then what happened to all the rest of the energy? So maybe this is a good time to compensate for the ungiven credit in this slide, which is only partial. There aren't all the proposition here, but we're gonna I'm gonna do the following deal. So because I didn't give you credit, I'm going to give you more credit than I gave you before. So I think that your mechanisms are in fact so efficient that rather than bringing the energy from 10 to the 53 ergs to 10 to the 51, they'll probably bring it all the way down to 10 to the 50. And what's left is the shocks. So I'm giving you even more credit. But there's, of course, the chance that you like the way you tailored your theories, and you like them to bring it back, to bring you down to 1% and not 0.1%. So for that chance, we also have our own explanation, and Tzvi was presenting it. That's the elliptical accretion. If elliptical accretion happens, then we don't even get to any of these scenarios, at least at the beginning. Now, I don't know to tell you how much elliptical accretion can carry on its own. If we would make a bet, I would probably agree that it should do at least half of the logarithmic distance between 10 to the 53 erg and somewhat less than 10 to the 51. And the remaining should probably be either any of these or some combination of these that would do the other half of the distance to what we actually see, to what we actually see from accretion, if what we're seeing is the outer shocks. So I think I didn't even use my 2 spare minutes, right? Well, I don't need them.
One of the points you didn't put on the ways you can reduce it from 10 to the 53 to 10 to the 51 is reducing the star's mass and partial disruption.
Right.
And the IMF is biased towards low star masses. Even for top-heavy IMFs, the slope is just different. But it's still biased towards low mass stars. And partial disruptions are going to be more common than full disruption. The second thing is that if the Eddington limit needs to be respected in the sense that it cannot exceed the Eddington limit through the disk, the shape of the light curve is going to be very different if you're exceeding the Eddington limit. And it's going to look something flat and then having a decay at much later time.
I agree. But we're not seeing any flat part of it.
We do see things like that, but people are unwilling to say that those are TDE because they don't look like your standard transient. They last maybe a year above the Eddington limit, and then they decline. So, those might exist where you have things that are supposed to be releasing close to the 10 to the 53 ergs of energy, but the Eddington limit is respected. The third point I just want to make is we do see some evidence now for winds coming from TDE suggesting that the Eddington limit is actually being at least flirted with. So there's 14LI shows evidence for outflows. PS1, 11AF showed this magnesium 2 feature that seemed to be leaving at 15,000 kilometers per second. So, I just would make the argument that there are indications of the Eddington limit being respected and perhaps the energy problem not being as severe as it's being portrayed to be.
Yeah, I agree. I think that it's an open question, and it's interesting to see what we'll gather once we are willing to let go of some of the pre-assumptions. And I think this is happening as we're talking or during this last year.
You given examples of flares lasting a year. I couldn't quite tell whether you knew that there are such examples or whether they might possibly exist.
I've seen them from pan stars, where there are maybe 3 or 4 examples of AGN turning on to a flat level staying on for maybe 2 years and then having a sort of power law decay afterwards. And they're attributed to AGN activity, but they're not.
Now you spoke about AGN. Are they AGN continuing and they just get brighter for a year, or are they really dark before and after?
That's the proposal is that they've gone up in flux by a factor of 50 from at least prior to when they go through an active state. It's not clear to me if they have signs of AGN activity prior to that, like weak AGN activity. I think it's an open question actually. 14LI, for instance, is a radio source prior to having the disruption that we're all claiming, suggesting that it actually was a low luminosity AGN prior to turning on as a tidal disruption. Chelsea McLeod is the one who's done some work on this in CanStar. Some of these flares that turn on for a while and then flatten off and then decay. I guess what I'm just trying to say is that we are picking, maybe not on the power law aspect of the transient, but we're picking on the flare aspect of the transient, the fact that it peaks and over a relatively short time scale then decays. And I think when you see the Eddington, in principle, if the disk is limiting you, you'll just go up to Eddington. Maybe you can have a logarithmic increase above that level, and then you'll decline. And so we're observationally biased against selecting those particular kinds of.
No, but sorry that I have to cut you because we have some other questions. My remark on that is that let's focus on the event that we see. And the event that we see, we don't see the Eddington limit. So
we do see the Eddington limit. We have winds, right?
the winds are not at 10 to the 53 Hertz.
They're not at 10 to
The
the
winds
53.
are 10 to the 49, 10 to the 40, 10 to the 50. They are not at 10 to the 50 Hertz. So there is a limit to the level that one can twist the data to fit the model.
On the topic of Assassin 14LI, how does the circularization paradigm deal with the X-ray luminosity from this TDE? In your view, is Assassin 14LI an unusual TDE in which circularization was strangely efficient, or is this something that naturally occurs and is just blocked by viewing angle? If it's the latter, it seems like reprocessing to some extent is inevitable.
Yeah, so I should have said that this is mainly based on on the optical to UV events, which are the majority. Obviously, the X-rays are where we do see X-rays, especially if we see a lot of energy, is either a different mechanism or a special viewing angle or so. So this is based on thinking about the majority of the events and not probably two events where we do see X-rays by now.
Brief comment, because it seems to me that if there's a fraction of events in which the paracenter in gravitational units is large enough that the shocks occur at large distance, and we can argue about the distribution of that quantity, and I think it's not at all clear, where the peak is, but to the extent that it seems likely that there are some of them, then there will be these shocks at large distance. And generically, that's also one of the few regions in the whole system where the cooling time is not incredibly long. So if there's heating, and the cooling time is basically of order the mass return time, then there ought to be light. And the light you'd expect looks like this.
And I concede that you should expect light from the circularization shock directly. Like, I think that is an important point to make. It should be a contributor to the result light. I just disagree that you can completely get rid of the disk component of the problem. That's basically my main quarrel with the present solution.
So let's assume that the outer disk gives 98% of the observed emission, and that there is some additional component which contribute to the visual, and some other component which contribute to the X-ray. So if we agree on that, I can be of satisfaction.
Well, it's not clear.
I suggest that the organizer should give another 2 minutes to everyone that agrees with the suggestion.
Okay, I think that we're running out of time, so one more question.
Yeah.
So I mean, in this scenario, what you might imagine would be that you get this optical low temperature flare coming out at some stage, visualization. And then at some stage a little bit later, months later possibly, then you're going to get the disk coming in and actually accreting, and then you're going to get another flare, which is going to be in the UV and the X-ray form. And I don't think we've ever seen that UV flare with an optical precursor, or vice versa.
So
I don't see any reason particularly why these two things should be simultaneous in this case, which you do see quite. I mean, even the PS110J8, the UV and the optical flares is something.
So yes, Yair yesterday said that he was starting to look for a second signal from the accretion. My opinion is that you might not see anything, because if the accretion is according to the now so-called Jerusalem bagel, then you're not supposed to see that, or you're supposed to be to see a very faint signal, and if you're not sensitive enough, you'll just miss it. That's a possibility. It still needs simulations to be better checked.
So one last question while Nathan is setting his computer.
Another observed property is it's pretty smooth light curves without any RMS variability. You're only at like the 1% level, which is even less than what some AGN disks do. Whereas these shocks in the simulation, they're coming in, and so it's a stochastic process. So do you have an explanation for smoothing the light curve?
What do you mean by smoothing the light curve?
Well, I mean, you have these
It's
shocks
specifically the
coming in,
light
so
curve you
have
expect
spikes,
is
right, and so you should get a spiky light curve. If the optical photons are coming from dissipating the energy in the shocks, but in fact we see this extremely smooth light curve. So so it's just this one, nothing else.
I agree. It's a good question. It probably depends on should depend on the geometry of the flow that you produce, and what you're saying that we're getting a too symmetrical. We're suggesting that the flow is very symmetrical, maybe more than you might expect. So I agree. It's a caveat of this model.